decomposition. So we have an algorithm and sequential algorithm, and we want to run it in parallel. So we have to divide the computational tasks into a number of items that can be worked on at the same time. So these computational items are called the tasks. And we may think that the more tasks we have, the faster the program will run. But that is not at all certain. But one thing is certain. The number of tasks limits the amount of concurrency. For instance, in the ACA version of the preflow push algorithm, we have one actor per node. So, I mean, that will give a huge number of tasks. And an alternative would be, for instance, to have a C program with 2 threads where each has a queue of nodes with excess preflow and works on one node at a time. And then, obviously, we can only benefit from up to 2 cores or CPUs. So how can we divide a problem into tasks? If we look at the example of the ocean, we could have one task per, a set of cross sections, or one task per cross section, or a subset of a cross section, or one task per grid point. But what makes multi-core programming very complicated, well, not only that, actually it's just a performance issue. Well, that's not just, because performance is the whole point of using a multi-core. But we cannot know in advance what is the best decomposition, because it depends on which machine we are running on, and also of the input, of course. So what we can say is that we want to have as many tasks as the machine can handle efficiently. That's quite obvious, but it doesn't help us so much. But that's still the goal. And we should try to achieve that. And how to do that? Well, we need a new concept of portability, namely performance portability, so that the program is as fast as possible on all the relevant machines. Meaning with different parameters of a multi-core machine, such as different cache sizes, number of CPUs, and well, how these CPUs look, and the memories, and how they are interconnected. So how can we achieve that? Well, in our course, we have only the target for the parallelization is only the Power 8 machine with 10 cores and 80 hardware threads. But we could imagine, I mean, you can see if you get the same performance speed up on your own machine. And it's not at all certain that the one version of the program gives a certain speed up on I mean, relative to the number of cores, of course, on different. So what we may want to do is to write the program and take into account the amount of cache memory and the number of cores and well, different aspects of this machine. But we don't want to make it too detailed and too complicated. We want to have like a general nice idea how to get a good performance. Okay, not so easy, but let's look at an example. And okay, so let's say we have a program that works in 2 phases. So in phase 1, and it's related to the ocean, and we have in phase 1 there are n square operations that are performed on some grid points, and they can be done in parallel. And in phase 2, we want to add the values computed for each grid point. Okay, so how can we parallelize this? Well, the first phase can be done, I mean, each processor can get a part of these n square grid points. So we can get linear speed up, linear in the number of processors that we use. Okay, and then if we ignore communication and synchronization, which probably will be needed to add to this sum, if we have a sum variable, then we can add this as well in n squared divided by p time. So what we have done is to have linear speed up in the number of processors. But if we also consider synchronization, if we have a variable that we add to or accumulate to, then there will clearly be a data race. And okay, so that is a bit of a problem because there are n square such increments, and they must be done in a critical section, so the performance will be terrible. Actually, the parallelized version will have, okay, the sequential version will have time as 2 times n squared, and the parallel n squared divided by p for the first, and then n squared when we add with the critical region these grid points to the shared variable sum. Okay, so what will the speed up be at the most? Well, it's not very good. We can divide the slow divided by the fast. I mean, we can compute the time for the slow divided by the time for the fast. Okay, and it will be this, and it's less than 2. So we need to do something else. And what we often should have in mind is to compute results and store them so that nobody else is involved or has to care about it for the time being. So for this problem, it is quite clear that we can add to a local variable the grid points, and then we can add all these local variables taking, I mean, to add them together after phase 2 to get much better speed up. Okay, and for the preflow push algorithm, there are numerous things that we can do without bothering other nodes. And I mean, we have this huge graph, and we can spend a lot of time doing a partitioning of the graph so that we can find suitable subsets of the nodes. And then one task can be to compute the preflow push within that. Of course, the different subsets have to communicate since the flow is global. But having such a subset of nodes that are private to one task, then they can work without communication. I mean, writing to variables that other nodes, that other threads are interested in. But now we come to a problem, namely that preparing the input and dividing it into the parallel tasks may actually take too much time. So, well, I encourage you to try to figure out how you can do this, but it is not obvious that, I mean, there is a risk that if we spend too much time thinking about how we should divide the nodes into different subsets and tasks, then this can take too much time, so that the program will be slower. Even, I mean, one part can be faster, but another has been added. So this is a really interesting problem. Okay, that's all.